So we've got a disc rolling down an incline. Let's get a sketch of that. Here's my incline. Put a disc on there. Have it rolling. So I have some omega. And it's at an angle theta. It's rolling without slipping. And we've got an expression for the moment of inertia, I, of the disk, and we want the acceleration of the center of mass of the disk. So the disk, while it's rolling without slipping, is going to be moving, and it's clear that it's got some acceleration, since that's what they're asking for, but also because it's rolling without slipping down the incline. And corresponding to that, we're going to have some angular acceleration as well. It's got to be the rate at which it's spinning has to be increasing if it's rolling without slipping, and the rate at which it's going is increasing, the speed with which it's going down the ramp. Okay, we need a free body diagram for this. I'm going to draw that down here. So draw the disk, free of the surroundings, another perfect circle. We are going to need to be able to get that angle in the picture, so even though I've got it free of the surroundings, I am going to indicate the angle in there. So let's get theta in the picture. And now we'll put the forces on there. We get a weight force acting in the downward direction. I'll label that W for weight. We've got a normal force acting up in this direction, straight through the center of the disk, just as the weight force is straight through the center of the disk. And we'll have a frictional force, F sub s. And there's no reason to believe we're at threshold, so I can't use F sub s as equal to mu sub s times the normal force. It's less than or equal to that, mu sub s times the normal force. So we don't have an expression for F sub s. So there's my free body diagram. Is dotted lines to get the angle in the picture, so it's still free. I'll go ahead and indicate nearby but not touching an acceleration arrow and a curved sense of rotation arrow indicating the angular acceleration alpha. I think I'll start off by using the relationship between the torque, the net torque. I'll go counterclockwise about O, where O is the center of the circle. So the sum of the torques about O counterclockwise, as we view it in this diagram, is equal to I alpha. Clockwise. I think I actually want to go clockwise here. So change my mind on that. Sum of the torques clockwise is equal to the moment of inertia times the angular acceleration clockwise. Now the moment arm for the normal force, since it goes right through the center, is 0. The weight force is acting at the center, so it's 0. The only thing that's got a moment arm is this F sub s, but it's perpendicular to a radius, so the moment arm for it is just the radius, I'll call it lowercase r, of the disk. So we've got this, the whole torque is at F sub s times r, and that would tend to cause clockwise rotation, and it's equal to I, which can be expressed, I think I'll just write it as I on this line, but I alpha, where alpha is clockwise, so the alpha clockwise is just what I labeled alpha in the diagram. I'm gunning for acceleration, so I'd like to get that in the picture rather than angular acceleration. And we do want to say, when this thing rolls through some angle, I'll call it phi. Maybe it's better to do that on the sketch. So when our disk rolls through an angle phi, it's going to lay down a track that corresponds to this part of the circumference. Right here. Having an angle phi. And this, I'll call it a delta, just call it S. So starting from our starting position, I'll define this position of the center of mass to be, I'll call it 0, the 0 position, and the angle in that position to be 0, and then it rolls down to, like, this point is in contact, and it's traveled a distance S along the ramp, which is equal to the arc length right here, and it's also turned through an angle phi. I want to get a relationship between A and alpha here, and it's going to be through phi. So from the definition of angular measure in radians, I've got the relationship the arc length is equal to the radius of the disk times phi, and if I take two derivatives of that, I got S double dot, which is just A, because S is how far it's gone down the ramp as well as the arc length, and so S double dot is the second derivative of the position relative to my origin along the ramp, and that's just the acceleration, and this is R times alpha. So I got this simple relationship between alpha and A, the same one that you got for the tangential acceleration of a point on the rim of an object that's not rolling but just spinning. And so I can replace alpha with A over R where I have it. That's what I want to do down here. I'll replace alpha with A over R. So F sub S times R becomes, I'm also going to use that expression that they gave us for I, the 1/2 mr squared in place of I. So 1/2 mr squared, and then times A over R. One of these R's cancels out right there. The other one cancels out right there. Divide both sides by R. I got R over R, 1 on both sides. And so I can express, I think I'll just copy this down. F sub S is equal to 1/2 MA. Alright, I got a relationship between two unknowns, A, which is what I'm looking for, and F sub S, which is one of the forces here, from my sum of the torques is equal to 0 expression. Let's look for the sum of the forces is equal to 0. To do that, I got to break up this weight vector into components first. So I'll define an x-axis to be the one that we've been working with there. So this would be my y-axis, and I can say with that set of axes, which I'll just copy over here, X and Y, Y direction, X direction. I put the weight vector on there. And I'll put its components on there. One along Y, one along X. They meet at right angles. This is W total. This would be my WX, WY. This guy's looking a little bit like an omega, so let's fix it up. It's a capital W. Alright, I gotta figure out which angle is theta in this picture. I think I'll extend my x-axis down just a little bit, because what I want to do is draw a horizontal on here that'll help me out. Here's the horizontal I want. right there, and it helps me out because I can see by inspection that this is theta right here. From these two angles being equal to 90 degrees, you know, the three interior angles of a triangle is 180, so if one of them's 90, the other two have to add up to 90, and so this angle has got to be 90 degrees minus theta, and that makes this angle right in here the theta. That's theta. In that, I've got this whole angle from here to here is 90 degrees by inspection because it's the angle between the y-axis and the x-axis there. Alright, so now it's pretty obvious which one's which, so I'll go wx, I think might be all I need. Wx over w, with respect to this angle, that's the opposite over the hypotenuse, and by definition that's the sine of theta. So I got wx is equal to w, the weight vector, times the sine of theta, which, by the way, is just mg. Wx equals mg sine of theta. So I can draw a new free body diagram. It's interesting, I didn't use the weight vector before because it had no moment arm, so I was able to use that one, but now I got to draw a new free body diagram. I don't need to worry about the angles so much since I got the information I need, but this would be the wy vector. I got a frictional force up at right angles to that, call it F sub s. I've got the wx vector on there. And I've got the normal force over here acting straight up through the middle, so I can always slide a vector. Even when I have to calculate torques, it's okay to slide a force vector along its length, where as long as there's no deformation of the object, doesn't matter where along its line of action the force acts, it'll have the same moment arm. So that's the normal force. I want to do the sum of the forces. Oh, and there was some acceleration there. There's also some angular acceleration alpha. But the sum of the forces, this one should be looking like a straight line. Looks a little bit too curved for my liking. Let's try that again. There we go. Almost perfectly straight. So we got the sum of the forces in the down the ramp direction, down and to the right, is equal to the mass of the object times the acceleration in the down and to the right direction. Sum of the forces, okay, along this line, I've got two forces. Wx comes in with a minus sign since I go down and to the right, positive, so that's Wx comes in with a plus sign because it is down and to the right, and this one comes in with a minus sign. It's along the direction of the line of the shaft, but it's in the opposite direction to the arrow, so I get minus F sub s, and that's going to be equal to ma. I called a in the down the ramp direction. I called the acceleration in the down the ramp direction just a, and so my a down the ramp is just a in this replacement line. So I got essentially the title line there and then a replacement line, and this is it. I'm going to go ahead and substitute this expression for F sub s into this equation, so I wind up with Wx minus 1/2 ma is equal to ma. Essentially what I've got here, two equations, this one, and two unknowns, the a and the F sub s, a and the F sub s, and I got to solve them simultaneously. You can do that any way you want. I chose to substitute this one into that one. Essentially you tend to solve one, I call it the brute force method, where you solve one for one of the unknowns, the one that you don't know and you don't care about, and then substitute it into the other, and you wind up with an equation that only has the one unknown that you know, or you either know or you care about. I guess the one that you care about, it wouldn't be an unknown if you knew it. So adding a half ma to both sides, I get 3/2 ma on this side, so I got a is equal to, by this point I should have replaced Wx with what it is. we found it to be mg sine of theta, so that'll simplify things. mg sine theta is equal to 3/2 ma. So I got A is 2/3 g sine theta. Alright, let's call that the answer. We weren't given any values, so this one shortened up for us. I think I'll write that theta just a little bit neater so it's more obvious to you what it is. We got the acceleration in the down the ramp direction is 2/3 g sine of theta. If it was a block that was sliding as opposed to a disk, sliding without friction as opposed to this disk that's rolling without sliding, we'd have full g sine theta here, you might remember from other problems. So this one, the acceleration is smaller. Makes sense from energy considerations that we've discussed earlier as well. So we got for SAC 118, problem number 4, we find that the acceleration is just 2/3 g sine theta. I'm going to make a quick check and make sure that we answer the question that was asked. Find the acceleration of the center of mass of the disk, and that's exactly